Okay, so you can also think about the wave equation as essentially you begin at a point, you begin at a point in space, in n-dimensional space, where information is concentrated, and then applying the wave equation is essentially sending this information out along a time-evolving sphere, okay? Essentially, and the sphere evolves in space with the speed of the wave, right? With the speed of the wave, this sphere, which kind of encapsulates the information contained at that specific point, which is your initial condition, the time evolving sphere, which grows out of that initial point, is essentially carrying information according to the wave equation. Okay, and information is neither created nor destroyed in this process. This process conserves information. It's just a way of transporting information from a point from one sphere onto another sphere. Okay, now the idea is that the heat equation, on the other hand, if we begin with a point particle, okay, what's going to end up happening is that this mass, instead of just getting sent along a uniform mass distribution on a sphere, the mass is actually going to go from a point particle to a smooth Gaussian distribution throughout space, which is absolutely continuous with respect to the Lebesgue measure. So we're turning a singular point piece of information into an absolutely continuous Gaussian distribution with respect to the Lebesgue measure, and what that's going to do is it's going to destroy information. So you can see the difference in the wave equation as basically propagating information along a time expanding sphere. That sphere is expanding at the speed of the wave, and the heat equation as essentially diffusing information, which is actually a destructive process. So information is lost as it diffuses according to the heat equation. And then again, fractional calculus provides the ability to kind of tune the entropic dial between the heat and the wave equations to determine, okay, how much information do I want to be transmitted versus destroyed in this process. And of course, in real life, there's a balance of information transfer and propagation along waves, and also the destruction of information via the heat equation, right? Via essentially the second law of thermodynamics. So these two concepts are in balance with each other, and we can try to use the theory of optimal transport to better understand this interpolation between the heat and the wave equation given by fractional calculus.